Okay, cool. Cool to have you here. And looking forward to the tutorial as well. So this week, the community meetup is actually a collaboration together with MantisNLP, a cool consultancy company from Europe. Actually, I think Matt is actually living in Valencia, so it's quite close to Madrid. And yeah, we've been doing this cool blog series with them to highlight all of these fine-tuning techniques for RLHF, but also the alternatives. And I believe that Arnold is going to take the lead from their side and actually talk and share something about the data pipeline or the data paper that was released along with the models that were released alongside with that, and actually showcase and highlight what kind of steps they actually implemented within their pipeline to plan a clean SFT data set from, I think, 300,000 examples to roughly 6,000. But yeah, maybe Arnold can take the stage and kind of introduce what data is all about. And after that, Ben will take over from our side and actually show this new pipeline reproduced within distilabel 1.0. So the refactor, it's still in kind of beta release, so to say, but almost getting there. We're working on the docs and really eager to show that to all you guys. Arnold, feel free to take the stage.
Hello, good evening, everyone. So nice to meet you all. First time actually in the Argilla meeting. Quite excited to be here. Thank you very much for the invitation. As David already mentioned, I'm working in collaboration with MantisNLP. Matt is here, actually. Thank you for coming. It's a nice touch. So yeah, maybe, I don't know, Ben, how you'd like to do for the sharing. Maybe you'd like to share your screen. Yeah, we don't hear you. Thank you. Thank you. Maybe we can go to the top. So we have only a collab for material. I think it's better to have some slide. So just to make a quick introduction of the data paper and of the data pipeline that we've worked together on. First thing is just to put a global context and a little bit of overview of large language model magic and what has changed since late 2022, more or less, with GPT 3.5. To explain a bit what's the magic behind it, and we'll try to understand, okay, so now that we know there are a few LLMs that can be used for the industry, how can I adapt this kind of model to my own business case? We'll see in a nutshell a bit what are the drawbacks of this kind of method, and maybe that there are other methods that we can explore in a second time. And we'll see two different approaches. One that I will briefly consider, and the second one, which is more oriented, is the data and on a data-centric approach. And that I think should be the best if you want to fit, or if you want to instruct tune LLM to fit your business expectations. So just an overview of the LLM magic. I'm not sure about the background of everyone, so I will try to be quite brief, but I won't go too much into the details. But basically, the LLMs now from GPT 3.5 are a stack of two different tools. So the LLM foundation models. So I think if you've been working into the field for the last year, I'm sure you heard about BERT, I'm sure you heard about Roberta, GPT-3. So basically all those models, which are core foundation models, are the backbone of the LLMs. They basically transformer-based language model. And everything from here relies on this foundation. And actually, what's the main difference between the model that we got in late 2010s, I would say like 2018, 2019, is this second step which is called like reinforcement learning from human feedback. So the idea is we're going to leverage everything we learned into the foundation models, and we're going to add a new type of task, which is like the instruction tuning, that goes in 3 different steps. And the idea is to combine first the supervised fine-tuning. So if you're already familiar with fine-tuning in machine learning, generally you have a set of labels, you have a set of features, and you try to fit basically the features to the labels, okay, for text classification or any other classical machine learning. In this step, the main difference lies into that the fine-tuning dataset will be instructions as features and responses as labels. So what we're going to do is try to align actually the foundation model, which can generate text with like highly at a really good level, close to the human level, to make it answer exactly the way we want. Okay, and that's why we're talking about instruction fine-tuning instead of fine-tuning, because we're just going to align and to orientate the LLM towards a kind of behavior we would like it to have. So this is the first step, but actually I think there are the second and third step, which are basically the most important here, which is closer to the reinforcement learning with the reward modeling and proximal policy optimization. Just in one sentence, I will talk about the reward modeling, where actually what people did for the OpenAI, for instance, is that they generated for each of the instructions several possibilities for the answers. And from those possibilities, they ranked them. Why did they rank them? Is just to try to mimic the human preferences, meaning that depending on the instruction, maybe you like the responses to be more oriented towards, I don't know, like a usefulness, or maybe towards like less biases. So the idea of ranking is just to improve the responsive according to the instructions. Okay, so this is a bit like, and the first step, just a word about it, is just like the optimization program, which is reinforcement learning. On this side, I'm really not an expert, so I won't dive too much into it. But in a nutshell, I think if we can go down a bit. Okay, thank you very much, Ben. So in a nutshell, what do we have? We have foundation model, which were already available at first. And we have, from the foundation model, we have a process to instruct tune, okay, the foundation model. And what are the main steps is we need, again, to create like a curated data set of instruction responses, okay, just a bit like the one you're taking a look at. And you need also to optimize the answers according to the instruction to fit your preferences. Okay, so you see that we have a kind of interaction actually with the LLM, and that's why we're calling it like the human feedbacks. Okay, reinforcement learning with human feedbacks. So it looks a lot. At first, the first one of the created dataset, like classical machine learning or classical text classification for NLP fellows. And the main idea is, okay, so now I would like to use this LLM, which is really promising, to my own business case. Okay, I want to use it for my customer service. I want to create like a chatbot where my customers will be able to interact with. So how can I do it? If you use like maybe a closed large language model, such as the one from OpenAI or Claude or Gemini from Google, it's most likely that it's going to give you potential good answers, but it's not going to fit really to your needs. Generally, in terms of machine learning, it's most likely that the behavior of your model will be a bit different, which is done generally in the open source literature. So the main idea is, okay, how can I align this LLM to my business case without the data? Okay, so basically what we have is we come back to the first stage of machine learning. How can I create a data set of instruction tuning, of instruction responses, which will make able like the LLM to behave the way I like and to fit my business requirements? First thing is, we don't have a lot of, I would say, computational resources. We don't have a lot of people who can do what OpenAI did, meaning manually label everything, like create the data set, curate the data set. This is like a really huge problem in machine learning in general. But we had some research that came with what we call like the synthetic data. What is synthetic data? It's just like data which is automatically generated, meaning that you don't have to use like any human manual annotation, but you're going to guide at some point generation with LLMs or with other models. Just to give you a bit of overview, before the OpenAI, ChatGPT, Gemini, and everything, we already experienced this kind of model and this kind of strategy to improve the model, to improve model performances. The first one I'd like to mention is like the Dino from Chic and Shoots. And actually what they did is they used the GPT 3.5 to generate from scratch data sets to make a model on sentimental analysis. And actually generating the data from scratch, meaning that they haven't got like any data set to learn from, they outperform GPT 3.5 at some extent. So it's already been proved that this kind of synthetic data is already quite efficient. Second other paper is like from people from Hugging Face, I think, Scaro and Rush, where they were actually trying to use a prompt to guide the model better into how to take a decision. And what they proved is that using prompts can totally overcome the problem of data scarcity. So again, by designating, like by using prompts or by generating like data from scratch without any manually labeled data, created data sets, you can improve the model performance, and you can definitely have a model which is really good in a production environment. So let's go a bit down, please, Ben. Thank you. So how to adapt to the business case? This is, I think, the main answer, the main question of this talk, and the main question of what we're going to tackle now. So I think with synthetic data, we have two possibilities. The first possibility, which I will call like more is better, meaning that as we have the possibility to automatically generate a lot of data and a lot of labels, why don't we use a way to generate instruction, to generate responses? We do it like millions of times, and then we just train our LLM on the instruction responses dataset that we have. Okay. So this is an approach that actually has been done by, I think, the Stanford team for the Alpaca, where they use, I think, the GPT 3.5 or GPT-4 to create the instruction and the responses, and they got more than 50,000 instruction responses, and they train the LLM, which is based on Llama 2, to fit the instruction needs. Okay, so this is a way that you can go with, but I think the big drawback here is that it may be quite expensive when you want to fine-tune your final model. You have to take into account that this kind of model need like a big infrastructure generally, if you have an open source one, just as Mixtral or WizardLM, and you will need most likely to spend a lot of money into making like this fine tuning, and afterwards also for inferences, but here we focus more on the fine tuning step. And the second approach actually is a data-centric way of thinking. Okay, I think data-centric has been one of main path of investigation for machine learning, meaning that we're going to have into consideration that we can have equivalent result or even better results when we have a data set which is really well curated and that is qualitative enough to get the qualitative enough to learn from. Okay, so the main idea is with maybe 10 really cherry-picked data, you may be able to have like results which are close from fine-tuning on thousands and thousands of data points, okay, that has been generated. And this is the approach we're going to see here, which means that we're going to look at the data efficient instruction tuning for alignment, where our objective is we want to develop a LLM. We want to fit a LLM to our business case, but we cannot allocate like too many money into the development process. So it means that we want like to fine tune on a budget this LLM. And this is why actually the data is interesting, is because with only a few thousands data, okay, a few thousands cherry pick data, we can outperform some models with thousands and thousands, like thousands of data. And this is a bit the overview of this idea. So the idea will be using synthetic data first. So we have the capacity to create like thousands, maybe hundreds of thousands of data of instructions responses. But as we want to reduce the price of the development, we're going to pick like maybe a few thousands of the data within the 100,000 data we have. And we're going to cherry pick them depending on 3 different dimensions, which are key into the data selection process. So the 3 components are like the complexity of the instructions, the quality of the response according to the instruction, and finally, the diversity of the data, meaning that we want to have good data which is representative of the data set and which is really going to provide a new knowledge to the final model. So this is a bit the main idea of the data from a big data set that we have, like maybe hundreds of thousands of rows, try to select according to complexity, quality, and diversity, a smaller data set that we'll use for the instruction planning. If we can go a bit down, thank you very much. So just to introduce a bit the paper, as I was saying, for instance, the alpaca was using like GPT-4 to make some instruction response dataset. And actually with the open source community, you have access to, I think, around 200 or 300,000 rows of instruction responses. And so maybe you won't need everything. I mean, you most likely won't need all of this dataset, but you may try to cherry pick from those datasets which are already synthesized, which are already generated. You can try to pick up and to select the data rows that you're looking for. And I think from that, I'll let you, Ben, take over on the...
Myself, just unmute myself. Okay, thanks for that, Arno. That was a really nice context and background to the problem from the very beginning. Okay, so what I'm going to walk through is the implementation of the DEITA paper in distilabel. It's a really nice example to illustrate distilabel 1.0 because it represents a lot of represents the context for why we decided at Argilla that we need a main refactor like this, and I'll get onto that. But it's a complex enough pipeline that it overstretched the previous implementation and forced us to re-implement it in quite an exciting way. So we'll share this notebook, I think already, in fact. And the first thing that you'll notice is that this is installed from a beta release, and I think the real release will be out next week with documentation and everything. And this is just a pre-release for the community to try out and start to get your head around how it's going to work. So yeah, it's set up for Colab, and you can run it. It uses an OpenAI model, but you could also run it on an open source model, and it's got all the imports. You'll notice that this beta release doesn't have import shortcuts, so it's a little bit ugly in the imports there. But I'll first give you a primer on kind of distilabel as it is, just in case anyone hasn't heard of this package or isn't familiar with it. Distilabel is a package for generating synthetic data sets, as we've already heard about from Arno. And so let's imagine in a kind of simpler paradigm than data that you just have a generating LLM, which generates your instructions based on a prompt, and then a labeling LLM, which labels those prompts and gives them a score and a rationale, potentially, depending on the approach. And then we take those scores and rationales and we use those to distill down our data set and to create our data set. So yeah, these two LLMs label the rows in the data set, and we use the labels of the labeler to distill the data set into a smaller, higher quality data set. This is a simpler paradigm, as I've already said. And in the current implementation of distilabel, it is implemented in a simple pipeline with two steps, a generator step and a labeler step. They could be different LLMs, and those LLMs are given a task. And if you've used distilabel, you'll be familiar with this syntax, this implementation, where I say, okay, LLM, this is your task, text generation. Labeler, LLM, this is your task, you're an ultra-judge task. And so from our introduction into data, we know that actually we need a couple of different steps here, right? We need to generate on complexity, generate on quality. We need to score on each of those. And we also need to use embeddings to get data. So already that kind of implementation is just beyond the current distilabel version. So the refactor of distilabel 1.0, so the refactor of distilabel 1.0 brings in kind of DAG principles, right? So DAG principles, if you're not familiar, you can look those up in the link here. But basically, no, don't leave Colab. Stay where we are. Maybe just stay where we are. Oh, twice here now.
We are still seeing the collab.
Really? Sick.
Yeah.
Okay. Thanks, David. Okay, we incorporate DAG principles, which is like graph principles, where we have nodes in a graph that are connected by edges. But in distilabel 1.0, we have steps in a pipeline that are connected together. So we can say, as we look here in this sort of toy example, you'll see a more complex example below for data. We have a pipeline which we enter through a context manager. We give that pipeline a name and a description, and then we could say this is step 1, step 2, etc. And then we can connect those steps together, which says pass the data from step 1 to step 2. So this, in the kind of old paradigm or the more basic paradigm, let's say, could be generator equals text generator step, and then labeler, and we would say generator connect labeler. Okay, so that's our main principle of this refactor. And with this kind of extensible model, we can start to build more complex pipelines like data, right? And so they have two main components, pipelines and steps. And this is the first, this is an evolve instruct step, which is the first step in our data pipeline. And so what you'll see now is that rather than telling the LLM that it's going to have a task like text generation or ultra judge, we define a step, which is a process, and then we say which LLM is going to do that process. If a tool, which is, I think, quite cool now, is that we can have steps that actually don't use LLMs, and we just pass data to them and pass them on. So we can have quite simple, naive steps that move data around, maybe wrangle, manipulate, change columns, combine columns, etc. And we can build these up into quite complex pipelines. Okay, so our first step in the data pipeline then, and I'll work through these. The notebook, because of the nature of our pipeline implementation, is at the bottom. And so I'll work through each step of data with a kind of static code fence. So just to show you what that looks like. And then at the bottom, I'll show you the pipeline in full. So our first step is to generate our instructions. And so we use GPT 3.5 Turbo. We use GPT 3.5 Turbo and we pass it as the LLM to our step, and we give it a name. We give it a number of evolutions, and we tell it to store the evolutions. We tell it to generate answers, and we also tell it to include the original instructions. Okay, copy here. And then now we want to tell the LLM to make our instructions more complex, right? Step 2, evolve complexity. So we use this example here, which is the prompt from the paper, where we're basically saying, here's an instruction, go and make it more complex. And in distilabel, we wrap that up inside a step. And then we score that complexity as well. And we'll use that score in a subsequent step to filter and distill. In a similar way, we now look to quality. That's an infuriating jump there, sorry. We now look to quality, and we define a prompt that says, here's an instruction, make it of a higher quality. And we do a couple of things in that prompt to tell it not to go too far away. But generally, the LLM is given a basic instruction to make it of a higher quality, and we'll then score that instruction based on the quality. And so now we have instructions and responses, and we have scores for the complexity of the instruction and the quality of the response. And we want to increase the diversity of the data set. So as Anna already alluded to, this is a kind of problem with a number of these larger data sets, that there's a significant amount of redundancy. One facet being there are many very similar samples within those data sets, and therefore less information or less dense information for language models to learn from. One way that the data authors propose that we can get around that is by embedding the samples within our data set and ensuring that each sample has a sufficient distance to the nearest other sample. So we say it's sufficiently semantically different enough to the other samples in the data set. so that we have a diverse distribution of samples in our data set. Okay, so that's the steps of the DEITA paper.
Maybe you can duplicate the notebook. Might be.
Yeah, I think I figured it out now, actually.
Okay.
Yeah, sorry. Okay, so now we've got our complete pipeline, right? I'll go through each step because you'll see that there are other steps to manipulate data between these core data steps. We have our instruction generation, evolve instruct, as you've already seen here. We have our complexity scorer that scores the complexity of those instructions. We then expand columns, and we use columns here to identify that function, which is inside this expand columns class. And then we define output mappings and input mappings. So we say complexity scorer is expecting input named instructions, and we're going to map evolved instructions to instructions. And that's a key part of our refactored paradigm, that we can connect together our data sets through these mappings of input mappings and output mappings. And you'll see how these work here. So again, we're mapping that column to that column. And anyone that's used distilabel on more complex pipelines or try to use the current distilabel implementation on pipelines will probably be familiar with a lot of kind of column renaming and wrangling of these data sets. So I think you'll be familiar, you'll appreciate why we've built it around these input mappings. Okay, and then we move on to this quality scorer, and then we have another utility step where we expand columns. We incorporate a template here to generate a conversation, and then we generate our embeddings. And inside this, we use a LLM from transformers, and we define this here. And one thing that you'll see that's crucial in this refactor is that we've made it so that the LLM class contains everything related to that LLM. So when you are dealing with OpenAI or another API, that's things like API keys and configurations. And when you're dealing with a model that's running locally, that's relating to CUDA and Torch and these kind of things. So we've made we've limited down the functionality of the LLMs to really just that model and inferring with it. And then we've taken the step logic of the task itself and put that into these steps. Okay, and then the final step, or almost the final step here, we now have a series of steps within our pipeline, and we can connect those together, which is pretty basic here. We go through these steps and connect them together using this connect method so that each step passes on the data. And then we can run this through a parameters configuration like this. And what's cool about these configurations is that we can then serialize these pipelines, which makes them easier to share and to reuse. We can commit them to source control, which makes our pipelines more explainable and our processes more reproducible. We get a disti set, which is a data set, and then we can push that to the hub, and it has other methods for exporting and things like this. That's a kind of high level, well, that's the implementation of data in distilabel. We'll have some questions at the end, and then the latter part of the notebook just returns to the results and the application of data. And I suppose we're going to go to questions, but it would be nice to maybe go back to Arno, and if I could ask him a question about applying this in industry, and if you could give some kind of contextual examples of any projects that he's worked on or is going to work on, or the kinds of projects that would benefit from a data set like this, built with this data methodology. And then if anyone else has any questions about distilabel, David and I are here to answer those. That would be great.
Yeah, okay. Now, I think there's a couple of things I'd like to point out. So just before answering your question, what has been done in the DEITA paper is, if you remember when we were talking about LLM instruction tuning, we use a lot of labelers, and we use also labelers to rank the differences between your preferences between responses according to instruction. And actually in the data, it's a bit what has been done, meaning that they ask not a labeler to do, but a LLM to be able to rank each of the instructions and then each of the responses, making the reward modeling step. Okay, and I think this is why also it works so well, is because even if you have like low amount of data, you have like really good data, and you have already embedded in a way the preferences of your instruction and of your responses. Actually, this is like for me a good transition if you want to go for instruction tuning of LLM for your own business case. Generally, what really costs you a lot of money is to have the expert to create the data set for you. And I think that here, generally, what they've done is they created from scratch everything. But I have the sensation that what we can have is to add a bit of human knowledge here, like maybe by drafting a few instructions and a few responses with some expert, and actually try also to use the expert to rank some of the instruction and some of the responses, and based on this kind of knowledge, which is, I think, the really costly knowledge, you can try to generate the synthetic data and use the distilabel pipeline with the data, okay, with like a low amount of resources. And I think this is why it makes it quite interesting for application. I haven't applied it yet, but I'm quite sure for maybe generic problems that are customer cares or chatbot, it could be really relevant.
Yeah, I would agree also. And I think it's also, even if you would have the final step of the embedding filtering or something like that, and you already have a high quality data set with, let's say, 20K examples, you can still use a part of the pipeline, just do the generate embeddings and then do the data filtering. And then you'll end up with maybe a subset of the data, ensuring high quality, proper distribution as well. So it's, yeah, really versatile. And also the prompt evolution methods are interesting, I would say. And yeah, maybe I'm not sure if Danielle or Alex maybe have, because you guys have been playing around with this label pre 1.0 release. I'm not sure what your initial thoughts are on the new setup and the pipelining structure and these kind of things. Love to hear your feedback as well.
From my side, yeah, it looks a lot nicer. Obviously, I have to play around with it a bit more, and I was definitely getting myself into situations where I had to, how to put this, twist myself into knots, like trying to get things into the right way or whatever with more complex stuff. So yeah, this seems much, yeah, it seems like a nice improvement. Initial thoughts.
Cool to hear that.
Yeah, no, I think it also looks very nice. It's a bit of a cliche, but there will be a new paper next week that is even better than any of these methods, but hopefully this will be a little bit more able to just adapt to those. I do think it would still be very nice to have one of those examples that kind of implement very well-proven papers to show the steps, or potentially some higher level abstractions, but yeah, it looks really like a much more flexible approach.
Yeah, we do intend to start reproducing these proven papers as well. And one of the things that we've already noticed is that, for example, this specific implementation of data actually relies on the Evil Instruct paper or the Wizard LM implementation. So we also intend to find like a 1.1 release or something like that, where you can actually import a partial or a pipeline from somewhere else. For example, having the data pipeline in front of a new implementation that might be building on top of that. So yeah, you might be able to have this filtering step already predefined and importable, and then add that on top of an existing pipeline to also offer the flexibility there as well. So yeah, that's some things that we've considered.
That sounds very nice.
Arnold?
Yeah, maybe another comment. Actually, Daniel made me think of it. Maybe we'll have another paper that could come next week and the week after. What I'm really looking forward to is like a real industry application with the data. If I remember well, for instance, when the Dino paper came out, like to generate dataset from scratch, that was so promising that I tried it on my classification task also. So the idea was, on the Dino, they were doing like sentimental analysis. Basically, my task wasn't so different in the meaning that I wanted just to detect like complaints and queries into social networks, two basic linear classifiers. And actually, when I tried to apply exactly what they've done into my business case, it didn't work at all. I had the sensation that actually the model that we were using to generate the data was so overfitted on IMDb or Rotten Tomatoes dataset that it was really, really good into producing reviews of movies, but I really would like to see like the data then apply to something which is really specific, maybe in the legal industry or maybe to the medical industry, something that could really show that the domain adaptation is going to work also.
Yeah, I would say so too, especially for the prompt evolution or the filtering afterwards, because you still would need to, kind of be able to distinguish between these grains, complexities within like a industry specific data set.
One thing that I really appreciate about the new refactor that reminded me of Daniel's presentation from a month ago was the option to have like naive or functional steps rather than actually just LLM labeling, right? So like with your presentation where you generated haikus and then you use like a function to evaluate the haiku based on rules. You could have steps that do that. That's really relevant now to industry because you just downgrade the complexity and it potentially significantly increase the quality and accuracy or the precision of your evaluation if it can be measured in such a rule-based way. And that's quite cool, I think.
So would you be able to just add that as a separate step and then just define that as a Python function and it will just run? Or
yeah, so the current implementation is around basically a decorator of a function. So you just have a really simple step that just does this. So it's just totally extensible. But you can see that we already got these like classes for generic functional operations like expanding and combining columns and stuff, right?
That sounds very nice.
Loading data from dictionaries, some additional things. And everything is actually cached as well. So after every step execution, whenever your pipeline fails for some arbitrary OpenAI rate limiting API thing or whatever, then everything is actually stored locally in a JSON list format.
And it's also quite cool for sharing, right? Because like you can serialize your step and then share that with your data set. So you can say, oh, here's my haiku data set that I generated, and then here's the serialized function to evaluate it. So if you want to go and generate it with another model, you can evaluate it in the same way. So yeah, it's really exciting.
Cool. I'm not sure if there's any more questions or remarks or maybe something cool someone wants to share. But otherwise, then I would like to thank everyone for coming and hope to see you guys next meetup again. I think the next one is going to be in a month. And then DEITA Maran, a company from Valencia, is coming, and they are going to talk about their integration of Argilla within their system. They're doing some topic modeling and these kind of things. They'll actually showcase how they make the most of Argilla's new feedback dataset. So that's cool. I'm looking forward to it. There was one more question about the dataset size. Could you add some more context there?
The starting size or the finishing size? This is the...
So they started with 300K examples from different dataset sources, where like UltraChat and ShareGPT and some others, and they actually evolved them over time using this complexity eval instruct, and then ended up with post-filtered dataset of 6,000 examples. You can actually see that at the bottom, the data missile 7B one. And then they actually ran DPO on top of that with a random subset of the Ultra feedback paper of 10,000 preference pairs. So that's maybe the final question then. Cool. Thanks everyone for coming. Looking forward to your feedback on the 1.0 release next week.
Thank you very much.
Thank you.
Goodbye. Have a good night.
Thank you.
Bye.
Thanks, everyone. Bye-bye.